हो गया. Thank you. Let's wait for a few more minutes in case anyone else is joining. Then we'll start. I think we should get started. Hello everyone. I'm Ayush Kumar Tyagi. I'm PhD student at IIT Delhi. I work in intersection of medical imaging and computer vision. Um, yeah. So in this today's session, we will be looking into deep learning architectures. More specifically, we'll move to like CNN-based architectures and look for like maybe standard architectures which are already present and see like suppose you want to basically train your first CN based architecture, what should be the things you should be doing and where do you start basically. Yeah, so maybe we'll give you a recipe for what do you say, start like getting started with things very quickly, and what should be the learning rate, what architecture you should use, right? Those kind of problems we will look into. So, but before that, let's like take few questions, like problems, and then we will move to the coding part. Yeah, okay. I hope I am audible, right? If I am not audible, just let me know. Okay, let's get started. So, like suppose we are given a neural network which has two layers, right? And we are using a cross entropy as a loss function. Uh, but what we do is like we initialize the weight of both the layers W1 and W2 with 0, right? So the question is, will network will be able to learn anything or not, right? So what do we have? Let's write it down more formally. So for a given input, we have a network, a layer which has parameter w1, right? We apply some sort of a non-linearity g here, and then we pass the output it is z1, the pass the output to layer 2, that is w2, and the output is basically z2, which is actually equivalent to y, and we compute loss between y prediction and our maybe your ground truth, and in this particular case this loss is basically crossing truth, right? So what I have done is, like, we have initialized everything with 0, right? uh, so what I've done is I've initialized weight of both the layers with 0. So what we see that, like, we want to see is like what is the impact, and what do you need, uh, what additional information we have is we have g is a activation function, and it is basically a tan h based activation function, right? And like, how does the tan h look like? It basically looks like something like this, right? And it ranges between -1 to 1, and tan h of 0 is basically 0, right? So this is the information we have before starting the problem. So we want to see how uh, the model will behave once we start training it. So the question we are asking here is, will the model be able to learn, right? Any guesses on will model be able to learn? Okay, anyway, I'll just get started. So suppose you have, you want to compute the derivative of loss with respect to w2, you want to compute derivative of loss with respect to w1, right? So what is the loss? uh, the loss will be some sort of intermediate term. We are basically applying chain rule here, right? And this is the intermediate, and z2 is basically equal to w times w2 times uh, this g of z1. Let us assume this is some sort of alpha, right? z2 is basically w2 alpha 2. Okay, so now if you want to compute derivative of z2 with respect to w2, it is basically computing derivative of w2 alpha 2 with respect to w2, and it turns out to be alpha 2, right? And how do you define alpha 2? Alpha 2 is basically uh, g of z1 g here is tan hyperbolic, and z1 is basically the multiplication of x and w1. That means x1 w1, right? uh, uh, so we what we have done is we have initialized all my weights with 0. So w1 is essentially 0. So tan h is, and this turns out to be 0, right? So your derivative of z2 with respect to w2 will become 0, and since it is in a form of a product, your this term actually is equal to 0. So your derivative of loss with respect to w2 becomes 0, right? So that essentially means that like your weight w2 is not impacting whatever the changes in the loss. So any change in the value w will not like have an impact in the output, right? So it's some sort of a redundancy we are introducing in the system, right? Similarly, let's see for what is the impact of w1 in the output loss, right? So what we do here is we will similarly apply chain to w1, sorry, derivative of loss with respect to w1 is will have some intermediate terms, right? Let us see. We are at this point and we want to go to at this point, right? So what we have is first will be an intermediate term of z2, right? Okay, come here. Z2 is basically dependent on our output of input at this point, that is alpha 1. Alpha 1 is basically dependent on z1, and z1 is basically dependent on your w1. So this is the chain rule that will follow. uh, this is the chain rule we will follow, right? So we will see that like what is the term which is basically dependent on uh, maybe w1, right? So this first term is basically the law, the derivative of cross entropy. Second term, uh, second term will be equal to, let us see, so it is alpha 1 z2, right? And so it is alpha 1 z2 is basically w2 alpha 2. So this is actually alpha 2 only. Right, and it is essentially w2, and the weights of w2 are initialized to 0. So that means that the whole term is basically 0. So this essentially means that this term is equal to 0, right? Since every other term is in the multiplication, your whole loss, derivative of loss with respect to w1, that is the gradient we are computing, becomes 0. So when the gradient actually becomes 0, then there is no update, or like your output is not actually changing with respect to your weights. So the model will eventually not learn anything, right? So there is no change in weights, there is no updates in the weights, right? So the model is actually learning nothing, and your loss will always remain same, so it will not reduce. So if you remember the update equation, so maybe wt plus 1 is w gradient of loss with respect to w, right? Since this term is always 0 in our case, there is the updated weights will be equal to your new weights. uh, like the updated weights will be equal to your old weights, right? So there is no change in weights, there is no learning happening in the system. So if you initialize everything, uh, everything to 0, right? So initialize weight of initialize the weight of all the parameters to 0, then there is no learning happening in the system. So what should be the ideal way? So there are different type of initialization methods. One is you can actually use random initialization, then a normal initialization is also used. Then there is something called as Xavier's initialization. So there are different form of initialization. I think whenever you are initializing in PyTorch, they use Xavier's initialization method. So right, so be aware that like you don't initialize every your parameters to like 0, right? I hope it is clear, right? So like we had two layer system, um, and both the layers had are initialized with 0 weights. We saw that like there is no change in the loss with respect to w2. We saw that like similarly there is no change in the loss with respect to w1. The gradient is 0 in both the cases, hence there is no update happening in the system, due to which model is not able to learn anything, right? Similarly, suppose you want to what do you say, initialize your parameters with constant, like the same same number, right? So what will happen in that case? Any ideas? So all the weights are initialized with the same value. So suppose of if all the weights are initialized with the same value, all the neurons will be learning the same thing, right? So there is no distinguished learning for each neuron. So all the neurons will be learning the same thing. So that's why it is essentially you will be training a single neuron for, but it's repeated over the multiple layers. So what you want is like you generally want a random initialization of weights. The next question is, why is CNN better than fully connected uh, neural networks for imaging data? Right. So the first thing is it parameter efficient as compared to the neural networks? So what happened in neural network? Can you show the answer? Can you show answer to question 2? Yes, the question answer to question 2 is this. So the network will not be able to learn the data as all the neurons will learn the same things. Since all the neurons are initialized with the same value. Clear? Okay. So next is, why is CNN better as compared to neural network for imaging data? So first thing is number of parameters we are using. So suppose you have let us say 28 cross 28 cross maybe one image, right? And you want to identify certain patterns in this image. So how does the neural network work? you flatten it into a single vector that is has a dimension 28 cross 28 cross 1, right? So the dimension will be a single flattened vector, and you pass this information to this vector to a neural network to predict something, right? Instead, what CNN do is you look for patterns. So what we do is like we have multiple filters. So you can actually create multiple filters, and same filter will be used to identify a particular pattern in the whole image. Suppose there are maybe two dogs or maybe two flowers are there, right? Right. And this first filter is essentially learning to detect flowers present in the image, right? And what we are doing here is we will be pass like traversing the whole image to see if there's a flower present. We will be performing a convolution operation, and with the same filter you will be able to identify a flower wherever it is there. So same filter can be used uh, uh, to is triggered whenever it sees a flower, right? And that actually makes things parameter efficient, because you don't need to look for flower at different locations. So the location actually become irrelevant in this case. The pattern becoming more important, right? So that's why the same filter can be used in multiple images at multiple locations to identify if there's a flower present or not. Makes sense, right? Okay, great. Similarly, CNNs are basically designed for have a better inductive bias. Okay, so what uh, CNNs actually do is like whenever you actually filter, flatten out an image, so you take away the spatial localization present in the image, right? So you what you do is like you treat each pixel at as its own, whereas uh, like CNNs, they treat i- structures or features based on the specialized localization, right? So you can see that if there's a feature called petals, right? It should have some sort of a circular structure, and the circle will be close to where the pattern was identified, right? So CNN actually takes into account your localized information, the location based information, whatever is there, CNN actually takes into account, and that's why it has a better like inductive bias. This is what the inductive bias is, right? So you basically have some sort of localization based structures which are inherent to your visual images wherever you're taking, either you're taking the satellite images or you're looking into the medical images. So these structures are spatially correlated, and CNNs actually look into the specialized neighborhood to identify those structures. So whereas the neural networks, they actually flatten out everything, and now uh, like at suppose a point at this place, if you flatten it out, the point at this place and this place will be next to each other, right? So suppose this is row 10 and this is row 11, and this is C column 1 and this is column maybe 28, last column, right? So this point and this point will be close to each other whenever you are basically flattening it out. Whereas if you are actually using CNN, these uh, they will be far apart, and the points which are close to each other will be triggered. Hope I didn't complicate it too much. Yeah, but the crux is like uh, the specialized information or spatial information around the object. CNNs actually make better use of that, whereas the neural networks actually take away that, since it works on the basically vectors. So you flatten out everything. That actually becomes the issue rather than the advantage. Yeah. So since like it's computationally efficient and also have the inductive bias, so it becomes what you say CNNs are actually better. So the answer is both A and 1 and 2. The next is basically like suppose you are given an image, input image of 64 cross 64 cross 3, and you have a filter 3 cross 5 cross 5, and if you do actually a convolution operation, what should be the output? So the formula is basically n minus f plus 2p by stride plus 1, right? So n here is your image size, minus filter size plus 2p is your padding, and then you have a stride information. You don't want, generally want to keep the symmetry, right? Right, so let us see if you actually feed in the information. Right, by stride is 2, then you have plus 1, right? So if you solve it, it should come out to t, and by 2. So this you actually take it to the upper limit. This will come out to be maybe, I guess, 28 point something. You take it to the upper limit. Right, is the your filter size, and since the number of channels will always remain same, so the convolution is here is happening at the, what you say, in the x and y. So why are we taking padding is equal to 0? Because it is you. So for now, I think we are assuming it's a 0 padding. Like if you are assuming at this point there's a padding equal to 1, then the equation actually changes, and the same equation, like you can feed in this information into the same equation, and then only thing that changes here is you'll have plus 2 here, right? So it becomes 61 by 2, right? Yeah, you can actually take 0 padding as well, but the equation, so the crux here is, I think, what the formula we are using and how we are actually feeding it. So it becomes 30.5 plus 1, you take it to upper limit, so it becomes 32 cross 32 kind of a setting. So whether you take padding or not, you can actually see. For me, actually, it's not clear. For me, it was not very clear. So 0 padding is what I don't know, like for me it was not very clear. It might be like you don't pad at around the thing, or like you pad with at least one uh, layer outside. So I just wanted to show both the variations. I hope it is clear, right? I mean, in exam, maybe like if that's the case, you can actually ask for clarification. Makes sense, right? But like the takeaway here is this one, the formula. So let's move to the next one. So what is the key benefit of pooling layers, right? So if you take, it will be 30. Yes, then it will make it to 29, 29.5. Then you make 30. If we have 29, then we make it 30. Can you just you might want to unmute and say in which part. If you are saying that, like if you're actually not taking parting, then it become 29.5. And then you can actually take it to 30. So the answer is 31. So rounded, is it rounded up to 32? Yes. So that's why actually. So you cannot actually have. So these are basically the physical filters, right? So you cannot have a filter which is 31 point 0.5, right? Like either you do it at a higher or you make it a one step lower. So generally you take it one step higher, right? You actually go to the ceiling. Correct. 29. So you round it up to 30. Yes. Yeah. Makes sense. Or like you want me to go over it again. So why 30? Why not 31 in that case? Uh, I mm, you can, but what people generally do here is, so the filters are like you don't actually, you can actually have like 31 as well. So there is no rule that it cannot be 30, like 31. But uh, for in this case, so let us write it away. So it can be 30.5, and at this point you can actually decide whether you want to take it to 30 or maybe you want to take it to 31. So I mean 30 is more common, that's why I went back to 30, you can actually take it to 31 as well. But since this operator is basically, I think it is the floor operator, and that's why actually they have moved to 30. So you just like define what with what nomenclature you want to proceed, and then just stick to that. Let us actually have one more case, right? So if it is, so let us see if we have 28 comma 28 comma 3, and you have same filter size. What is the filter size here? 5 comma. Right, minus 5, and suppose you have padding is equal to 1, 2 divided by stride is actually also 2, have plus 1 here, 28 minus 3, till 1 out of beta 12 point something, 4.5 plus 1, so we will actually make it to 13 cross 13 also. All yeah. I think I'll just, I think I should recheck actually, because people can actually say, because since it is 5, right, like one can actually say it, you can actually make it to 14, 14 cross 14 as well. So in exam they don't give these edge cases, but let me check how does PyTorch do it in case of this, in case of like we are actually at the boundary. So maybe in the next session we will actually come back to it and then rediscuss. So next question is basically what are the key benefit of pooling. So we are basically doing pooling to like reduce the size of our feature dimension. So it actually reduce the half, like the size to half. So suppose you have 2 cross 2 pooling filter, so you convolve it, you just take one sample from it, right? So what it does is it reduces parameters. Also it helps in translation invariance. So what happens is whenever you are actually reducing the size of the image, you are reducing the translation. So suppose the object was here and the another object was here, right? So whenever you start pooling, they actually become very close to each other, right? So if like the object is like scaled, maybe it so suppose this object is like moved to this space, maybe this object is moved to this space, right? If you are actually like reducing the dimension, just think that like you are actually looking at the object that is very very uh, close to each other, right? So slightly any shifting operation, any shifting operation should be like is taken care of, right? Like so uh, like maybe 10 pixel shift toward the right, or 10 pixel shifting toward the left, or maybe upward or downward shifting, that effect actually becomes neutralized because we are actually reducing the overall feature space, right? Maybe the correct word is basically the receptive field, right? So everything actually mapped to the same. So uh, if from this place you can actually go to, both of them will be mapped to the similar place, right? If you actually go back and see, you can have multiple objects that might be appearing, right? And all of those can be mapped to the same point, right? So that translation invariance actually get reduced when you're actually doing the pooling operation. So yeah, and since it basically reduce the parameter, there is the computational side to it as well. So all of them are actually correct. So the last question is basically, so you have a convolution neural network, right? And you have two type of features. So like suppose you have shallow layers and the deeper layers. So the initial layers are called as the shallow layers, right? And the deeper layers are called as the like anyway are called as the deeper layers. So what the question is asking, what type of features these type of layers are actually capturing. So the correct answer is basically low level features are being captured at the initial stage. So let me just see. So this edge information, some texture information is captured at the initial layer, and the deeper layers actually start making sense out of these edges. So suppose you are actually let's say you are actually doing a task for maybe human face, celebrity face identification, right? So what people initial layer will do, they'll actually go for maybe maybe skin texture here, hair texture here, right? And what the later layers will do, they'll start to make sense of what are the nose types, are there ears, uh, nose, ear, right? They start detecting these part of the face, and as you move to the much deeper layer, they start to make sense of like uh, for that particular person what were the characteristics of the face. So as you go deeper, it you are actually looking at a bigger picture of the image, right? As we have as we saw that like this pixel will actually correspond to a very big area in the original image, right? So the deeper layers actually start to basically make sense out of knowledge which we have acquired through the initial layers. So initial layers will actually go for edge detections, or maybe texture detections, or maybe color detections, right? Or maybe some sort of a patterns which are present in the maybe images, or any type of jewelry a person is wearing. So maybe if the person is actually like wearing some nose pins, right? So CNNs might actually go and start detecting if there is a nose pin, and then it will start to correlate that this feature might be like biased towards uh, the woman. So the takeaway here is the initial layers actually look for like very minute patterns or structures, and the later layers, right, the deeper layers actually start to accumulate this information and start to make sense out of it, right? So there is, let me see if actually I can find a paper that has this information. So I hope you can see my screen. So now actually we will look into like how to actually make these things to work, right? So we will be using PyTorch to create a classification architecture, and then we'll train it and see that what are the things you need to remember whenever you're creating the image classifier. So for this we are using the MNIST dataset, so it is already present in so if you actually import like from torch vision datasets, it is already present in uh, this dataset class. You can actually call like dataset.mnist, and it will automatically detect everything for you, right? So what we have done is like we have created a very small neural network based architecture, and then we will actually see a CNN based architecture for the same problem. So how do you actually go and create a CNN, like a normal architecture, and like PyTorch? You define it as a class what you can actually name it anything, class MLP, right? And you import what are the modules are there, right? So so Torch has a neural network like module which you can use as torch.nn, and it has a function called linear. So it basically initialize linear layer with input this, and this is the output, right? So in the first part what we do is like we initialize all the layers. So this is the constructor part, right? So you are defining in my case I am using three layers, right? So first layer is actually taking input 784 dimensional input. So how does the 784 come into picture? So the image size of each of the image is 228 cross 28. So if I flatten it, it becomes 784 cross 784, right, cross 1. So that actually becomes my input. So I'm feeding in 788 84 dimensional data, and then the output of this linear layer is 256 dimensional, like 256 neurons. Then the layer 2 actually takes into 256 neurons out, and then like the output is basically 128. So the final layer actually maps 128 neurons to 10, right? And 10 actually comes from the number of classes we have. So in MNIST we have 10 classes, right? Um, and that's why we are actually doing a 10 class classification in this case. And so what you do is like you have a forward function which uh, flattens your input, right? So torch.flatten actually does the job, like with if you, even if you provided it as it a image 28 cross 28 image, and it simply flattens it, right? And then what you do is like you have a fully connected layer 1, you pass it to that, you have you apply non-linearity on top of that. The output is basically given to layer 2, you apply non-linearity on top of that, and then the final layer, right? In the final layer you don't actually apply any non-linearity. So the loss function actually does that job for you, right? So whenever we will define loss function, we will actually look into it. In Google Colab, there is a functionality of using GPU, right? So if you have GPU, you can actually put your model and the data to GPU, and it basically trains faster. So what you do is like you define any transforms are basically some sort of augmentation. Suppose you want to resize everything into some particular size, you can actually provide it here, or maybe color contrast and those kind of operation if you want to do, right? Those operation you can actually use define under this transform.compose. Right now what I'm doing is like I'm transforming everything into tensor. So because like for training actually I my whole data should be in a form of a tensor, not in the form of numpy, right? And whenever actually you can actually normalize it as well, or even if you don't normalize it, it works fine. So but in case of suppose like you're training for natural images, you want and you're using some pre-trained architectures like ResNet or something, you want your data to be normalized to the space where uh, in the same way the data which was used to train ResNet was normalized, right? So first is train data set. I've defined the data set, right? And the second is basically the data loader. So first there are two part of like creating the data set into the format that can be fed to the architecture. First one is you define how are you actually going to read data set. It can be from your local directory, or uh, like it can be downloaded on the go, right? uh, the second part is basically how you are actually going to feed it, like batch it. So you might have studied about different batches to cast, like batch size 1, batch size 64, whatever it is, right? So what you do is like you chunk out the data set into certain batch sizes, and then you feed it to the architecture. So this tosh utils data loader does the task for you automatically, and you can actually define batch size, and if you want to shuffle, just make it true or false, right? So what we generally do is whenever we are training, you make shuffle is equal to true, whereas whenever you are testing, so you don't want any stochasticity there, so what you do is like you make shuffle is equal to false, right? So now we initialize our model. So model is equal to MLP, and you shift the model to device, that is basically CUDA in our case. You define the loss function. Criterion is equal to cross entropy loss, and then you define what kind of optimizer you are using. So you I generally start with Adam optimization. So you can actually check for stochastic gradient descent and everything, but Adam works very well. You define learning rates as well, and what parameters are you going to optimize. So model dot parameters are all set of parameters which are going to be updated, right? So you define how many epochs you want to train it, right? So then for each epoch you start to go over your whole training data. So you traverse over whole training data, right? You what you do is like you move your data to the devices as well, and then what you do is like you feed data to model. It predicts some output is given to the loss function. Loss function then actually uh, like with loss you actually compute the gradient. So this loss dot backward actually does the task for you. So you compute gradient at each layer, right? And optimizer dot step is that weight update step, right? So where with a particular learning rate you update your parameters, right? So these are the uh, two steps which are very essential. So loss dot backward is basically performing the back propagation, right? And optimizer dot step is kind of updating your weights. uh, yeah, so you can actually keep a track of what is your loss over the few image like samples, and then you can actually check what is the performance of your model on the validation data or maybe the test data, right? So I just trained it before joining the session. So like initially the loss starts at 2.31, and after the end of first epoch only it reaches the accuracy of 96.52, right? And we are computing the accuracy on validation data. So if you train it for more epochs, what will happen is it will start to improve 97.31, 97.48, 97.65. Yeah, maybe if you like train it for sufficient epoch, maybe 20 to 50, you should be able to get a very good performance close to 99% of accuracy. So uh, since the data is very simple, even the MLP actually works very well. So this is the visualization I'm getting. So true is basically what was the ground truth label. Prediction is basically what the model is predicting. So of all the cases, it is predicting correctly. I think only for this one, it is making error, and you can see that like it's a very difficult example. It can be 5 or maybe, yeah, 6 or so. So right, so this is how you're basically you train your model. So next I think we will move for, we'll take the same example and update the model to a CNN based architecture. Any questions at this point? Okay, so what we are doing is like we're doing the same transform, data loading steps are very similar to what we have seen earlier. Only change is the network architecture, right? So like what we are using a 2D convolution operators in this case. So neural, so and it's the same module. So torch.nn actually has different you can actually call different functions which uh, do the convolution operation for you. So the first parameter is basically one, so it's the number of channels your input data has. So in our case we have only one channel since it's a grayscale image. So the image input data dimension is basically 28 cross 28 cross 1, right? That's why there is one channel. So now what I want is I want to learn 32 channel in this layer, right? And I want my model to have a kernel size of 3. You can actually have a kernel size of 5 or 7 as well, and I want padding is equal to 1. Similarly, you define different layers as well. So the next layer, what is happening here is the number of input channel will actually become 32 because you are outputting 32 channels. So there should be a match between the layer one output of layer 1 and input to the layer 2. So what is happening here is this actually remain consistent basically, right? So you are taking 32 channel, outputting 64 channel. You can actually keep the kernel size 3, padding is equal to 1, right? And then you define max pooling layer. You have different linear layers. So linear layer is basically uh, at the end you want to do predictions, so that's why you flatten out whatever the features you have learned, right, and do a prediction on top of that. So I am mapping, so this was the dimension which I'll get if I flatten out my feature space, right? What I do is like I map it to slightly lower dimension, and then I map this lower dimension to exactly the number of classes I require. You can actually use dropout function as well. So what dropout does is basically it drops 50% of your uh, connection between the layer. In this case it will drop your filters, right? So you'll not every filter will be active at every pass, right, and every forward pass. So this this is where you define all the layers or you will be using. So now in def forward, this forward function, you will see that how the data flows through your architecture. So what I do is like I'll pass my input data to the convolution function, convolution first convolution layer, right? Then apply a non-linearity on top of that. I pass that, it will return me some output, right? This output I'll feed to second convolution layer, apply non-linearity on top of that, then I apply a pooling operation. So this is in our case max pooling operation. After pooling operation, I simply flatten out the whole like feature space, right? And then what I do is like this flatten out feature I'll pass to layer 1, apply non-linearity on top of that, in order to ensure that model does not like overfit very fast. I apply dropout here, and then output of this is basically fed to final layer, that is FC2, right? This actually becomes our network architecture. Similarly, I'll be using the same loss, which is cross entropy loss. Model dot parameters, like all the parameters of the model will be updated whenever I'm actually taking optimizer dot step, and the rate at which these will be updated is defined as the learning rate. So one of the important hyperparameters whenever you're training your architectures is this learning rate. So like for this it works fine, and I really want that the training converges very fast, but I generally start with 1e minus 1e minus 3 or 1e minus 4, so that these are the two learning rates which actually works very well. Similarly, like the training loop actually remains same, so you have your feed, you are traversing over whole data for like suppose 10 epochs, right? Passing on the input data, model predicts your output. You pass output and the ground truth label to the criteria, it computes some loss. Based on this loss, you compute the gradient of the network. Then you do optimizer dot step. You update the weights based on the gradients we have computed, and then it moves to the next step, right? And there is a evaluation loop as well, where like you train, and so the essentially thing is like you want to keep your training and the validation data separate. So you train, because eventually with sufficient capacity the model will overfit on your training data, so you want your validation data to sort of mimic what the real world data will look like, right? So like you evaluate on this validation data, and you can see that like the loss will start to reduce from 22.22 to 0.03, I guess. Yeah, and the test accuracy which we are getting here is like 99.15, and this is actually within 5 epochs, so this is, yeah, very good. Yeah, similarly, if you can see that the prediction, so this was the like the error case which we were getting in the neural network, right? The DNN part, right? So in this case, CNN is actually predicting correctly, so this is good. So yeah, so this is two parallels which we have drawn between a neural network and a CNN, and you can see that the CNN actually works better, right? And if you go to much more complex data sets, maybe bird classification, bird identification, so the rule of thumb is basically go for CNNs, and even within the CNNs as well, just initialize everything with what do you say, pre-trained architectures, because they are anyway trained on large data sets. We will see in one of our notebooks how we can actually do that. But before going there, so there is something called as the weight decay. So weight decay is uh, in the optimizer, there is a like parameters is which is basically weight decay, and weight decay is basically the regularization parameter. So you can actually map it to L2 regularization, and if you want, and this is basically the weight of like that regularization factor. So this you can actually map it to lambda, some sort of a lambda times regularization, maybe L2 regularization. So if your model is actually overfitting very fast, right? So you want so what is essentially happening here is you have model which has a very high capacity, and there are very limited patterns in your data to learn, right? That's why the model is kind of overfitting. So what you do is like you can actually use L2 regularization to reduce the capacity of the model so that it doesn't like overfit very fast, right? It should learn different patterns. So you can actually use this parameter in that case. I think we have discussed about the regularization and this in the last lecture. So, but in case anyone has a doubt, like I think this is the good time to ask. Okay. So, like there is a task of like so there was a data set called as the ImageNet. So right, and there was uh, in early 2010 there was a competition which was going on, like on this ImageNet data set. So people were actually using some sort of CN like DNN based architectures at that point, or maybe like CNN based architectures people have started, but not that like deeper architecture, very few layers. So AlexNet was the first architecture which actually outperformed all the like models at that point of time, and it became state of the art. So it actually gave a very big boost in overall like the performance in the this like ImageNet data set, right? So this is the paper. If you want, actually, you can actually look into it. ImageNet classification with deep convolution neural network, and it introduces what kind of hacks they have done. So this is the architecture they have proposed. So you have like you have higher like what you say, they started off with very high like resolution filters and eventually reduce it to the lower dimensional, so they start with 11 cross 11 cross filled kernel, right? And then in the lower, like in the deeper layer, they have a smaller size filter, so 3 cross 3 cross number of channels. So that that's why we thought that they thought that, like, since initially you want to actually identify bigger patterns, so let's keep the these filters like fairly large, and then because in the deeper layers we are already at some sort of abstraction, you can do the task with smaller size filters as well, right? So they did different type of data augmentation as well, right? So, and this was the paper actually which showed that the initial layer what these filters are learning. If you can see, I hope you can see, right? You can see that these are the patterns the initial layers were learning. So these are essentially the edges, or maybe color operators, like edges of the color, right? So those things basically are learned by the initial layers, and then actually in the later layers actually make like assemble everything into one place, and then they do the classification. Yeah, but I think this is a good paper if you want to get started with. Yeah, and so this PyTorch hub actually has the already pre-trained version of this AlexNet, right? And what generally people do is either they start with AlexNet or ResNet like architectures. Like ResNet 50 is maybe the state of the art whenever anyone try to do like a classification problem, they start with ResNet only, right? But if you are like want to use AlexNet, what I would recommend is like use this pre-trained architecture. So this pre-trained architecture is basically trained on like millions of images, and it has already learned different type of learned to extract out different type of edges or maybe filters, right? Maybe features, right? So if you actually look into the PyTorch, just search for AlexNet PyTorch, and it will actually give you this like link to how do we actually load. Similarly, you can actually define this as well. So, like this notebook actually does the same task. So, what we have done is like maybe suppose you want to like build AlexNet from scratch. So how do you actually do it? So in this case, we are using CFAR10 dataset. So it has 10 categories, right? So this dog, cat, car, aeroplane, some bird, horse. So these are the different categories of this present in this data set, and you want to actually do a classification task on top of that. So this is the architecture of AlexNet, right? So you have initially you have a higher kernel, so you have kernel size of 11, right? And what you do is like you reduce the kernel size over the time, and you increase the number of channels you are using, 64 to 192, 192 to 384. Then like you start to reduce it, like so 256 to 384 to 256, and then at the end you flatten out everything into like a linear layer, and then pass it to this linear layer, and then just do the classification task, right? So number of classes here is 10, right? If you print this model, it will actually give you what is the architecture of this, and like you can the training loop actually remains same, and you can see there is a reduction in the loss accuracy somewhere close to 64%, right? And if you train it for much more epochs, you should be able to get the better accuracy, right? So there is one more thing I want to actually introduce you. There is something called the grad cam. So uh, like these uh, models are actually called like considered as the black boxes. So in what region these models are actually focusing on, you don't know, right? So the GradCam is one such library which actually helps you in this. So if you actually search for PyTorch GradCam, so it will take you to this GitHub page, and let me just show you. So what does GradCam tell you? That like suppose you have a dog classifier and there's an image where it has dog and the cat. So the model is actually focusing on the dog in this case, right? Suppose you have like maybe the classifier or the label associated to this is cat, so the model will actually focus on this region to basically label it as cat. So there are different region in the image which models need to actually focus on, so that like it is able to correctly classify like give a good indication what object it is. So GradCam actually look into the gradients, right? How where the gradients are active, right? And to map it to the class level. So suppose you see, yeah. So suppose the category here is dog, right? So the GradCam actually look at these features, the feature of this dog, to identify it as a dog. So GradCam actually tells you what features you want to focus, or the model is actually focusing on to classifying it into a particular category. So for this is basically the interpretability analysis. So once you are done training your model, you can actually see that whether the model has actually learned good features, and just try to understand that on what basis model is saying something. So it become very important in case of suppose medical imaging, where like you're saying that like the person, the biopsy has cancer, but there is no indication that how the model actually come up with that. So if you want to see what region the model is actually looking into, you want to use these kind of libraries. So GradCam is actually one of them. So I think like the implementation wise it's very simple. So it's basically a package. You can actually install it using pip install GradCam, and you can simply pass the information, right? Uh, like in the form of cam, right? Your input answer and the target, and it should basically give you an image that you can actually visualize. In this case, it's kind of looking at, I don't know what it is. It looks like a cat, and it's basically looking at the features of cat. And anyway, this model is not properly trained, so I would say that uh, like you train it for maybe like higher epochs, maybe 50 or 100, and then see that whether the model is yeah. So just see that like if model is able to identify the regions where on basis of which it is able to identify this is a cat or a dog. Similarly, there is something called the ResNet. So this is a very popular framework or model which is called as the ResNet. So it's deep residual learning for image recognition. The paper came up in basically 2015, right? And the whole idea was like they introduced this residual learning, right, where like apart from learning through weights, they are actually using the skip connections as well. So this skip connection actually helps you learn much deeper architectures, right? So there was the issue that like you are not able to update the weights in very deep architectures, right? So this this residual connections actually help in that case. So this is on the paper, right? And if you want it, you can actually look into it in term of what you say, PyTorch. So this is the architecture, and you can actually use this PyTorch hub to actually download or use this, right? And there are multiple variants to it. So ResNet 18 is basically 18 layer ResNet. ResNet 34 is basically 34 layer ResNet. ResNet 50 50 layer. 101 and 152 layer. So based on your application and the complexity of the data set, suppose you have a large data set right? And which is fairly complex, you want to go for a higher ResNet. So suppose ResNet 152. But if you have limited data and the complexity of the data is fairly limited, you want to try first with like 18, then maybe 34, and then 50. Right? I think 50 should be sufficient for you. Yeah. So like in this case, I'm actually loading the ResNet architecture. So model.resnet actually does the same job for you. And if you say pre-train is equal to true, that means that it will load the pre-trained architecture where you have the weights which are trained on the last data set of ImageNet, right? So it becomes very handy since you don't want to train everything from scratch. So what you do is like you instead load weights from a pre-trained architecture and then fine tune it to much of much refined space and take it to your problem. Like suppose you are building for maybe satellite flood detection, right? In the cases in the region where there is a flood, right? So you, you might be training on satellite images. The model is actually trained on natural images. So what you want to do is like you want to take it and then fine tune it on your satellite images and then uh, like use it but use it as the backbone of your architecture. So you use this architecture to extract out features, and on top of that you might want to add few layers of CNNs or maybe direct classification layers, right? You can actually decide how many layer you want to train. You don't want to train the whole ResNet, right? You might just want to train few of the layers, right? Maybe 10, 15 layers that you want to train. So just you just unfreeze those 10, 15 layers and then keep the rest of the layers intact, right? And on top of that, what you do is like you uh, extract out these features and then just feed this feature to a neural network and define the number of classes. In this case, the number of classes is 2. It's basically dog versus cat classification problem, right? So but if you feel that like you need more layer, just you can actually create an architecture where you initialize everything into the init function, uh, right, and add few layers, and whenever you're doing the forward pass you define everything in the way you want to do it, right? And the training and the validation loop actually remains same in most of the cases. So uh, I think it's basically boils down to how you're using the architectures, what kind of learning methods you're using, maybe uh, how you are basically tuning the hyperparameters, um, a knowledge of whether the model is actually overfitting, underfitting, those those analyses actually become very relevant. And if you actually want, you can create everything from scratch as well. This module actually does that for you. So last, actually, I just want to show you. So here, what we have done is like we have created model which has different architecture. So you have LANet. This is basically created by Jan LeCun. Then LXNet. You have different. This 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 is VGG16, I guess, right? And the important takeaway here is this graph. So whenever you're training your models, there is one thing which I recommend is just always plot your accuracy, training accuracy, and the validation accuracy along with your training loss and the validation loss. If you can actually see this point, right? At this from this point you can see that there is a increase in the validation loss, right? So this is the point where you want to stop training. So uh, this is the point where the overfitting starts. So these indications will actually like happen when you have a sense that how the training loss is basically progressing. So always check for validation loss and training loss. Training loss generally keep on reducing, right? There will be a point where the validation loss will start to increase. So let us say, so this one blue, right? It starts to increasing. uh, for maybe LXnet it starts at somewhere here, and maybe for VGG16 it starts somewhere here, right? So these are the point where it will start your overfitting process. So what you want is like your best performance of the model should come before this thing, right? So this is the minima you have achieved, and now it will the loss is actually increasing. So the model is basically defining itself for the training data only, so it will not do well on the your test data. So you might want to uh, save the best model based on the validation loss, and the point where the validation loss is minimum, that model you want to save and use it for maybe the further analysis. And it actually gives a good sense of how the training is progressing. So like in some cases the training is very slow, you might want to increase the learning rate. In some cases the training is very fast, right? Maybe it just simply shoots uh, within 2 or 3 epochs. Might want to slightly reduce the learning rate in that point, so that like it actually learns different type of features, so that it doesn't bypass any learn any bypass. So yeah, so I mean, I would say just learn, always create these uh, plots, so that like you have a better understanding what is happening under the hood in the training. So there is something called as weight and biases. There is something called as the weight and biases, and this is basically free, and so if I can show you something. Just a minute. So I mean, like you can actually use, uh, so you can use this weight and biases to log your like runs. So whatever the loss you're computing, whatever the accuracy you're computing, you can actually feed it here, and then it keeps a like log of all the training you have done, and you can actually define different type of metrics. Uh, here as well, right? All the parameters, all the information which was required, all the metric you want to compute, you can actually keep a track of them here. So this is like a one place where you will be keeping all the your training and your, what do you say, uh, like your progress for a project. And you can actually create multiple projects in this case and use them. Maybe let us see. So this is for maybe for it was for detection, right? And all different losses you can, so you can actually compare losses across different runs. What was the best performing model? What was the model which was performing which has the best particular metric, F1 score, precision, recalls, everything can be put into one place. So this you can actually use. So I use it frequently. So this is weight and biases, and it is free, so you can actually like log things better. There is one question. Sorry, I missed it. So Tushar has a question that how would someone new know that she is familiar with Python? Is understanding the logic behind doing anything enough, or are you required to write full code by yourself? Say, uh, since at the starting I would encourage you to write your full code, right? But like once you understand things, there are methods like maybe ChatGPT or Gemini. People make use of them. Only thing is their logic has to be very clear, right? What you want to do and what you want to build has to be very clear. So like and in and more importantly, so like if you want to debug things, right? Like so because for a simpler code, ChatGPT and those methods, these language models will do very good job. But once you are actually building something more substantial, which require much deeper understanding than all the things here which you have learned by writing everything from scratch will come into handy. So yeah, I would say like for starting, at least write one code with like DNNs, right? Deep neural networks. Second, write one code with CNNs. So it will actually give you a very good indication that how does this filters work, what is the output you are expecting, how what is the output you are getting, and then you can actually design your architecture, that what should be the input to the second layer. Just write it down over on a notepad and then try to implement it. So it actually gives you a very good indication. And try to implement this just go over this ResNet or like this AlexNet like architectures and see if you are able to understand everything. So that actually makes things very clear for everyone. So when I started, uh, like I faced very like difficulties in CNN based architecture because you don't like see what should be the output, and you have to specify what padding I'm using, uh, like and how many channels I want to use. But once you make two or three architectures of CNN, then I think you get a sense at how things operate. So a simple like DNN based architecture and then one CNN or two architectures, I think should be good enough for starting. And training loop and everything, data loader, these things are actually like in simpler problems are like pretty straightforward. But once you move to some complex problems, you might want to spend a good amount of time understanding what's happening under the hood. Anything else? I think this is all I have for this week. So I just wanted to give you an introduction to like how do you actually train your first CNN based architectures and what are the different architectures which are present. Like if you have any doubt, I think this is a good time we can discuss, or we will close it here. Anyone? Any doubt? Like anyway, like I would say, I would recommend to go through the notebooks, try running them, inspect each module, and see if you find any errors or if there is something which is not clear. Like you can like go over it. Meanwhile, I'll just put down the papers which we have discussed in the chat in case anyone is interested. Weight and biases. PyTorch hub. Yeah, I mean, just follow the links. Spend some time them with like understanding them. It will basically make your the whole process very like smooth. So I would say I can actually give you a tutorial next time on how do you actually integrate weight and biases into uh, your current code. But I think it is fairly simple. So maybe anyway we'll do. But meanwhile, just have a look at the resources I've shared and go through the notebooks. See, like just train your model. Will feel a sense that it is learning and you're kind of starting to get a hold of how to make these things works and try to play around and tune different parameters, maybe try changing the kernel size for cnn's and see if it gives you error and then try to fix it. That like suppose instead of 3 cross 3 kernel you have to use only 5 cross 5, how do you actually modify the architecture? So try these things and I think yeah, I think it will be a good learning experience for you. Anything apart from that, just let me know. And also any questions, any doubt, I think we can spend some time, we have some time here, we can discuss. If you have any question, just let me know now. Anything apart from this session also is fine. If you're facing any difficulty in understanding a topic, that also we can discuss in maybe in next session, but you might have to inform me prior. Okay then, we will close the session here. Thanks everyone for joining. If you have any suggestions or comments, just put it in the discussion channel. Or if you want to suggest any topic need to be taken in the next mod session, so just put it there. Okay, thanks. Thanks.